Hello everyone. In this video, I'm going to explain machine dependent assembler features. That is the next topic of module 1 of SSCD. Here in this topic, we are going to consider the design of assembler of SICXE machine. Here, the design of the assembler depends on two features. We call them as machine dependent features and machine independent features. Machine dependent features means the architecture that is supported by the machine, like how many and which are registers are there, what are the various addressing modes that are supported by the machine. See, all those come under this machine dependent features, and these we are going to consider while designing the assembler. We also have machine independent features. That is the next topic of this module. Okay, let us start with this that is the topic, machine dependent assembler feature. Here, as I said, we are going to consider design of assembler for SICXE. What are the dependent features? Here, this supports the various instruction formats that we had discussed in the previous topic. The various instruction formats are format 1, format 2, format 3, format 4, and these are the different fields that I have explained in the previous video. And the various addressing modes. Okay, totally 7 addressing modes that are supported by this machine. And in the assembly program for SICXE, we are going to make use of various symbols such as @ symbol, hash symbol, plus symbol, comma X. All these are used to indicate various addressing modes. Okay, just for an example, I'll show this SICXE code. Here you can see that these are the mnemonics and these are the operands. In the operands, you can see for this LDX instruction, LDX hash 0, it means that this instruction is based on immediate addressing mode. Then we have here one more symbol, that is the plus. It means that this instruction has to be assembled using format 4. If there is no plus, say for example LDX, LDA, we don't have plus here, it means that it will be assembled using format 3 instruction format. Then we also have one more that is table comma X. Suppose in the operand, if we have this comma X, it means that this instruction has to be assembled based on indexed addressing mode. Okay, then if we don't have any symbols, comma, @ symbol, all those, say for example in this JLT, we don't have any symbol, then this instruction will be assembled in format 3 based on either PC relative or base relative addressing mode if we don't have any symbol. So these are the different meanings that are used in SICXE program. The same thing is explained here, and see, this is for the programmer understanding how the machine understands the different addressing modes that are used in the machine instruction in the object code. So those are indicated by these flag bits NIX, BPE. Here all these flag bits indicate which are the different addressing modes that are used in the machine code. Based on this, the target address is calculated. Even all this we have done in the previous module, previous video. Let me continue with the next. Here in this that is a topic, in this particular topic, we usually get a question. What question? You will be given SICXE program and you will be asked to write object program for this assembly program. Okay, you will be asked to write object program. So that is what is the question that you can expect from this topic. Now how to start? Okay, before starting, let me explain the meaning of a few statements. As you know that start is an assembler directive, so there is no machine code, but it indicates some that is instruction. What is that is indicated by this start? It says that the object code, okay, that is generated by the assembler should be loaded at that is, it should be loaded in memory starting at address 101A. So that is what is indicated. So likewise, you also have the other assembler directives, that is RESW. We also have other assembler directives, that is RESB, word, byte here, but we have only RESW. The meaning of RESW is reserve the specified number of words. Here it reserves one word. One word in SICXE machine means it is 3 bytes. So likewise, we also have one more, that is RESW 5000. What it means? Reserve 5000 words, contiguous words. So that is in words, so totally it will reserve 5000 into 3 bytes, each word of size 3. So totally 5000 into 3 bytes contiguous locations will be reserved. That is what is indicated by this RESW 5000. Similarly, we also have 723 1. Okay, so that is, yeah, we have the meaning of the these different assembler directives. You observe this assembly program also has one new assembler directive, that is the base. This assembler directive base, it indicates that the register B has to be used as a base register, not general working register, and this B will contain the address that is assigned to symbol table 2. You will have somewhere here in the label field, you have, yeah, here we have label table 2. The address that is assigned to table 2 will be in base, that is a B register, and register B has to be used as a base register. That is, it has to be used for computation of a target address based on the base relative addressing mode. So that is what is the meaning of base assembler directive, and for this base no machine code is generated. Okay, so these are the different assembler directives we have, and similarly we have other executable statements like LDX. LDX means load X. Load X hash 0. What do you mean by that? 0 has to be loaded into register X. What do you mean by this? Next, LDA hash 150. This value 150 is in decimal, so hexadecimal representation, okay, that is a binary representation of 150 will be loaded to accumulator. Next, we also have one more, that is plus LDB. The meaning of plus LDB is it has to be assembled using format 4, and hash table 2 means the address of table 2 will have to be loaded to B. Then what do you mean by add? What do you mean by add table comma X? Meaning of add table comma X is it should add, it indicates a add operation which all content of a accumulator and content of a memory location whose address is computed as address that is assigned to table plus content of X. Okay, so that is what is the meaning, that is what is the operation that is indicated by add. So here comma X indicates that this instruction has to be assembled based on indexed addressing mode. So that's all the different meanings of these instructions. Okay, let us continue with the problem. Okay, you are supposed to write the object program. How to start? You imagine that this is given to the assembler, and what the assembler does, it will perform two passes. In pass 1, all the addresses are assigned. All the addresses are assigned for all the instructions as well as for these different symbols. And once it is done, it will be given to the pass 2, and what the pass 2 does, it will generate the machine code object for each of these instructions except the assembler directives, and object program will be generated, as well as assembly listing is also generated, but only object program we are supposed to write. What is that object program that is generated we are supposed to write now? Okay, so we will start with the pass 1. And one more point, you will also be provided with the opcodes for different mnemonics. Okay, so this is provided, program is provided. Okay, assembly program will be provided. Okay, we will start now. So if it is given to the pass 1, what is done, it assigns these addresses. So you are supposed to write all these addresses. How to start? You see what is first instruction, that is sum start. Okay, 101A, meaning is the name of the program is sum and starting address is 101A. That is what has to be written at first. Okay, for the next instruction, this is executable instruction. Executable instruction will be converted into the object code and its address is 101A. Okay, so now move to the next instruction. Next instruction is LDA. For this you assign this address 101D. How this 101D is written, since this instruction will be assembled using format 3. Format 3 means it will have 3 bytes. Okay, 3 bytes will be reserved for LDX #0. So the next instruction will have an address. What is that address? 101A plus 3. So plus 3 will give you 101D. So that calculation you have to do in hexadecimal. Okay, next address 1020. Why 1020? Again, this LDA 150 will be reserved 3 bytes. So add 3 to 101D, you will get 1020. Next address you see 1024. Why it is 1024? And one more point you observe, 1024 is assigned to add, not for base table 2, because base table 2 is an assembler directive, so no object code, so don't have to assign the address. Okay, now we are seeing now why this 1024. You see here we have plus here. Plus means, as I told, the instruction will have to be assembled based on format 4. What do you mean by format 4? Total 4 bytes will be reserved. So if 4 bytes are reserved, 1020 previous address will have to be added with the 4. You will get 1024. That is the address for next instruction, add table comma X. Similarly, you go on verifying all these. Okay, now let me explain with this 1037. Okay, 1037 you will get after adding 4 to the 1034. Okay, now you see why we have 103A, because RESW1 means reserve one word means 3 bytes. 1037 plus 3, so you will get 103A. Okay, now you see we have a next value 4AD2. Why 4AD2? As I have explained, table RESW 5000. What do you mean by that? For this name, reserve 5000 words. That is what is indicated by RESW. It is an assembler directive, no object code, but it says that reserve 5000 words. So 5000, okay, total words. Since every word is of size 3 bytes, okay, 3 bytes, I have written the computation here. What 15,000 bytes you will get, that is in decimal. So that 15,000 bytes you convert into the hexadecimal. You see this, you see this, see this calculation. 15,000 bytes will be converted into hexadecimal 3A98. This 3A98 you add it to 103A, that is address of the previous previous instruction 103A and you will get 4A D2. Okay, next similarly with this, okay, 723. Yeah, 723. Okay, 723 means again reserve 723 words, each word 3 bytes, 723 into 3 you multiply, get a value, and that will be in decimal, you convert into hexadecimal, and that result you add it to 4AD2, you will get 534B. So this is how you go on assigning the addresses at first. This you have to do at first. Okay, do the calculation in hexadecimal. These values will be given in decimal. Okay, next. So once you do once you completed that, you have to proceed with writing the object codes. So that is what is the next task. I'll tell you how to write, but before that I will explain what do you mean by this object code 0540s. So this is nothing but a object code generated for LDX hash 0. See, we human being, we can understand what do you mean by LDX hash 0, but assembler, I mean machine, processor doesn't understand. It will understand this only the object code. How it understands? How it interprets. LDX hash 0 means load this 0 immediate value to the register X, and that is indicated using this object code. Okay, object code, now it is in hexadecimal, you write it in a binary. So this is a binary. How to write it in a binary? Each hexadecimal digit you have to replace it with the 4 bits, 4 binary bits. 5 you have to replace it with 0101. So this is how we write the binary representation. Since it is total 3 bytes, 3 bytes means it is format 3. In format 3, if you remember, we have 3 fields, opcode field, NIX, BPE flag bits, then 12 bits displacement. Okay, in opcode we have 04. 04 will be interpreted by the processor as LDX. Then it checks what are the flag bits that are set. It checks that I bit is set to 1. It means that it indicates that this instruction is based on the immediate addressing mode. Then in that case, the content of displacement will be, what is the content of displacement? It is 0. So 0 will be moved to the X. So this is how it will be interpreted by the processor. We know this meaning, but the processor will know find out what is the meaning of this instruction using the object code. This is how it is interpreting. Okay, one more instruction. See, JLT, we have one more instruction, JLT. JLT means jump to loop. Okay, when this less than condition is true. Okay, where is loop? Jump less than loop. You see this? JLT, yeah, we have here JLT loop. Jump to loop. Where is loop? This. Okay, execution has to be continued to this statement if the less than condition is true. See, where is this instruction? It is at the address 1024. Okay, how the processor will jump to address 1024? So how it finds out? Okay, you see, jump less than loop, and its object code is this, and it is written now in a binary, and it is format 3, and these are the various fields. This is a 6-bit opcode, and it says 38 means it stands for jump less than. Okay, then it checks out what are the flag bits. It checks that P is set to 1. What do you mean by P is set to 1? It is assembled using program counter relative addressing mode. If it is program counter relative addressing mode, in the previous video I have told that target address will be computed as content of PC plus displacement. Content of PC means address of the next instruction. The address of the next instruction is 1030, and displacement, content of displacement is FF4, and it will be added, and that addition again is in hexadecimal. The result is 1024. Result is, you can see the result is 1024. That means jump to 1024. Target address is 1024. This is how it finds out where to jump, where to continue the execution by computing the target address using this formula. Okay, so till now I explained the meaning of the object code, how it is interpreted by the processor. Now how to generate this. Okay, so that generation has to be done by the assembler. Okay, so that is what we are going to consider, how to write all these object codes. Okay, let me explain one by one. Okay, so we will start with the first instruction, LDX #0. Since LDX #0, we don't have plus here, so as I told that it will be assembled based on format 3, and since we have here hash, it will be assembled based on immediate addressing mode. And you write on this format 3 fields. Format 3 fields are 6-bit opcode, NIXBPE and displacement. You leave this NIXBPE in the beginning empty while writing. You have to do all these writings, okay, while finding the object code. Okay, you write in opcode 04 will be given, as I told, opcode will be given, so this is what is 04. Then since here we have found that it is immediate addressing mode, you write on the flag bits. Okay, E has to be set to 0. Why is set to 0? Because E indicates which format. If it is 0, it indicates that it is format 3. If it is set to 1, it will be format 4. Now it is format 3, you set to 0. And P, no program counter relative. B, no base relative, so that is why you set it to 00. No indexed addressing mode, so that is why you set it to 0. Then I, you have to set it to 1 because #0 is there, and N you have to set to 0 because no indirect addressing mode. Okay, if there is indirect addressing mode, you will have this @ symbol. Okay, so you will write all these flag bits. Write these flag bits carefully. Then #0 you have to write in the displacement field. Okay, so 0 you indicate in hex. In 12 bits, it's a binary representation, 4 bits, 4 bits, 4 bits, all 3 zeros in hex. Okay, now you write these binary representation. This is binary representation. You write it in a hex because the object code we will be writing in hexadecimal. Okay, how to write? Group the 4 binary bits, okay, and write the hexadecimal representation. So it is 0 here, 0101. Okay, it stands for 5, all zeros. Okay, so this is what the object code. I hope it is clear. Okay, now we will move to the next instruction. In the program, the next instruction is LDA #150. Again, you have to see that is there plus, no plus. So it will be based on format 3. Since we have hash, it will be based on that is a immediate addressing mode. Okay, and I also told that these values will be in a decimal. You better keep it written what is the hexadecimal representation. And one more point, while solving this problem, you keep the calculator with you, and have a scientific calculator that supports all these hexadecimal calculation conversion. Okay, so that's what is required during the exam while solving the problem based on this topic. Okay, so you convert 150 to hexadecimal, that is 96. Okay, since it is immediate addressing mode and it is format 3, you write this. Okay, what are the fields of format 3? 6 bits opcode, NIXBPE, 12-bit displacement, and in 6 bits opcode, write down the given opcode. You will be provided this 00. How do you write in the binary? First 0, all 4 zeros. Each hexadecimal is represented using 4 bits. Okay, next 0 you write 00. Actually it is 00, but it is 4 zeros you have to write. Since in format 3 these 2 bits are reserved for the flag, don't write 00. Okay, so you leave it blank. Actually you have to write all zeros, all 4 zeros, since these LSB00 are reserved for N and I. You have to leave blank as they are reserved for N and I. Okay, fine. Then okay, NIXBPE you have to write later. Then since it is immediate addressing mode, you can write this 96 here in the displacement. Okay, how to write a 96? That is 3 hexadecimal digits. This is 9, this is 6, and this is 0. Okay, now you fill the NIXBPE. Okay, how do you fill? E has to be 0, BP, all these XBPE, all these are set to 0, and only I bit you have to set to 1 because it is immediate addressing mode, and you have to set it to 0. Okay, once you are done with this, you group these binary digits, that is a group of 4 bits. Why group of 4 bits? Because each hexadecimal digit is represented by 4 binary digits. So this is how we have made a group, and write the hexadecimal, that is 0 1 0 0 9 6. So this is what is the object code of the second instruction. Okay, continuing with the next instruction, we have the next instruction as a plus LDB. As I have told, if there is a plus, it is format 4. Since we have a hash, it is based on immediate addressing mode. Okay, and here as in the previous instruction, we are not given immediate value, but we are given a symbol, that is table 2. So you know what is the value of a table 2, address of table 2. Okay, that is 4AD2 here. Okay, that's you have already written table 2. Where is table 2? This table 2 has the value, address 4AD2. So this is what the address of table 2, that you have to use it here. Address of table 2. Okay, address of table 2 is 4AD2. Okay, since it is format 4, write the format 4 of SICXE. So format 4 means 6 bits opcode, NIXBPE, and 20 bits address. Okay, then you fill it with a binary representation. LDB opcode is 68. How do you write 68? 60110. 8, how do you write? Yeah, 8 how do you write? 1000. Okay, you write 1010, but for the time being, don't write these 2 zeros under N and I because they are reserved for flag bits. Okay, you leave this portion blank for the time being. Okay, then you fill this 20-bit address. How you fill? You write this 4AD2 in this. How do you write? First 4 bits you have to set it to 0, then you have to write 4AD2. 4AD2. Okay, then you set these flag bits. How to set flag bits? Since it is format 4, it is indicated by the bit E. Okay, and there are no indexed addressing mode, no base relative, no PC relative. So you set all these XBP as 0. only E you have to set to 1. Okay, continuing with the next I. I you have to set it to 1. Why it is set to 1? Because it is immediate addressing mode, and N is 0 because no indirect addressing mode. Okay, so once you are done, you group those bits of 4, make a group of 4 bits and convert into hexadecimal, and this will be the object code. Okay, continue with the next instruction. The next instruction is add table comma x. Since we don't have plus, it will be assembled using format 3, and here we have a comma x. As I told, comma x means it will be based on indexed addressing mode, and since we don't have immediate and all, it may be based on PC relative or a base relative. So start to assemble based on PC relative. Okay, so how to start? First you write down this based on format 3 fields, that is 6 bits opcode, 6 bits NIXBPE, and 12 bits displacement. You leave this part blank for the time being. Okay, now you continue with the calculation. You have to fill this. What is displacement? What is displacement? If it is PC relative, as I told, if it is a PC relative, there is a formula. Target address should be computed as PC, content of PC plus displacement. Okay, what is TA and what is a PC, that we know, but we don't know what is displacement. So displacement is equal to target address minus PC. What is target address? Target address is nothing but address of table. Okay, address of table that you have to see the result of a pass 1, and it will give you 103A. Check out the address of table, check out this diagram. Address of table, yeah, address of table, yeah, we have here, and its address is what? 103A. You have to refer this and you have to find out what is the address of table. Okay, address of table is 103A. That's what we have to write as TA as 103A, and content of a PC also we know. Content of PC is 1027. What do you mean by PC? PC is a register that holds the address of the next instruction. Address of the next instruction after add table comma x. You see the diagram. You see this. After the table comma x, add table comma x. Add table comma x. Where is add table comma x? We have here. Okay, and its address, what is the next instruction address? 1027, and this will be the content of PC. I hope you are getting. Add table comma x. We are assembling this at this line, the content of PC. Okay, that is address of next instruction. Address of next instruction is 1027. Okay, so this value we are using. Go back that. 1027. Yeah, here we have 1027. Yeah, we have here 1027. This is what we know now. TA, what is PC? You make use of this. Do the calculation in hexadecimal. You will get 013, and after the calculation, you check whether this displacement within this range that is specified by, that is specified for PC relative. In PC relative, okay, so if you remember this, we have to use, okay, this table you have to remember. If it is a PC relative, the target address is calculated as PC plus displacement, and you have to make sure that displacement is within this range. Okay, minus 2048 to 2047. That's what we use this table. You have to remember that table. Okay, now we'll move to that. Okay, yeah, 013 we got this, and check is it within this range. You check whether this is in range. Actually we got it in hexadecimal, convert into decimal and check is it, yeah, it comes within this range. Now you assemble this. Okay, write this 0 1 3 in displacement field and set these flags. How to set these flags? E has to be set to 0 because format 3. B has to set to 1 because it is program counter relative. B is set to 0 and X has to set to 1 because it is indexed addressing mode, and N and I will be set to 1. Okay, normally in SICXE machine, if no immediate, no indirect, then they will be set to 1. So that is why I have written N and I as 1 and all these flag bits. Okay, so this is the content that is in binary. Okay, now you convert into hexadecimal, you will get 1BA013. So that is what the object code. You see this 1BA013. You have to write as and when that you get 1BA013. We are done till here. Okay, 1BA013. As and when you compute, you write under this object codes. Okay, now we are able to compute this. Add table 2 comma x. Okay, so it is calculated similarly. It is calculated similarly. You can pause the video and check it. Yeah, this calculation is a little bit more. Let me explain this. Okay, add table 2 comma x. Okay, as I told, start with the format 3 because there is no plus. Since there is a comma x, you start with the index, you assemble it using indexed addressing mode. Okay, so this is format 3. You write the content of 6 bits, that is given 18100001. 8 means 100000. Don't write under N and I because they are reserved for flags. Okay, compute displacement. Since it is format 3, you have to start with a PC relative and compute the displacement, and it is computed as TA minus PC. Okay, TA is address of table 2. What is PC? Content of next instruction. You verify, okay, all these values. Then you get the value for the displacement. You will get in hexadecimal as 3A8. Okay, you verify and that you convert into hexadecimal, in a decimal, and check is it in the range. That is for PC relative. The range is minus 20482 plus 2047. No, it is not in this range. So you have to again go for the computation based on a base relative. In base relative, the displacement is computed as TA minus content of B. Okay, the content of B you have to use. TA is 4AD2. That is nothing but address of TA. TA is nothing but the address of table 2, and content of B is 4AD2. Why 4AD2? You see the program content of B. Okay, content of B. See, as I told, base, this assembler directive base, meaning of this is B will contain the value of table 2. What is value of table 2? Table 2 is 4AD2. B contains 4AD2. That is what is the meaning of base table 2. Be careful with this instruction, and it says what is the content of a B. Okay, so this is necessary if you have to compute the target, if you have to compute displacement based on base relative. Okay, remember content of B is 4AD2. Okay, so that is how we have written here. Now you compute a displacement. Displacement is TA minus B. It is 0. It is in the range. That is for base relative. The range is 0 to 4095. It is no sign. It is unsigned. Since it is in the range, you write, you fill all these. Okay, under NIXBPE. E is 0, format 3. B is set to 1. P is set to 0 because base relative, X is set to 1 because it is indexed addressing mode, and normally, as I told, N and I will be set to 1. So these are the binary. Yeah, in displacement you write 0. In hexadecimal you write 3 zeros. And that is 3 zeros. You convert these binary bits in hexadecimal by grouping 4 bits. Okay, so this is how you will get 1 B C, all 3 zeros. Okay, so this is how we convert this add table into object code. Okay, continuing with the next, TIX count. TIX count, since it is it doesn't have any plus, so it will be format 3. Okay, write the format 3 fields. Then since format 3 means we are not sure whether it is PC relative or a base relative, so you have to start with a PC relative. And if it is a PC relative, how to compute displacement? The displacement is computed as TA minus PC. What is TA? TA is nothing but value of count, value of a count 1037. You check out that program, there you will find the count value is 1037. Check out that. Okay, then PC is address of the next instruction. It will be 102D. You just check out, as I have explained in the previous slide. PC is address of the next instruction after TIX. Okay, so it will be 102D, and using these two values you compute displacement. You will get A, and once you get, you check, is it in this range? Yeah, it is in this range, minus 20482 plus 2047. Okay, once you are done, once you are sure that it is in the range, you write down that in this format. Okay, that is a format 3. Fill that. How to fill? We have already filled this. Okay, 2C, 2 we have filled. C means what? 1100. Don't write 00, that is reserved for N and I. That's what I had told. And fill this NIXB P is 0, P is 1. Why? Program counter relative. B is 0, no base relative. X is 0, no indexed addressing mode. N and I are normally set to 1, 1. And in the displacement you fill with the A, that is 0, 0, A, and you write the hexadecimal representation, that is 2F200A. Okay, so we are done till here. TIX. Okay, next you convert similarly for JLT, similarly for plus STA RSP. Okay, so I have that slide. You go through that by pausing. Yeah, this is JLT loop, you observe. Okay, then you can pause and check it. If you have any doubt, you can clarify. Then we have STA plus STA total. Plus means format 4. Okay, no, yeah, E will be set to 1. All these XBP are set to 0. Okay, then no immediate, no indirect, so they will be normally set to 1. This is how we get object code, and for our SUB based on format 3. Okay, then yeah, we are done with the writing of object codes. We are done with the writing of object codes. Okay, the solving the problem is not yet over. We are yet to write a object program. What is object program? If you remember, object program is set of records, and according to this SICXE, this object program has to contain 3 types of records: header record, text record, end record. Okay, and this you have to start to write now. Start with the header record. So if you remember, what are the fields of the header record? That is very important. First column H, then next 2 to 7 name of the program, then 8 to 13 starting address, then 13 to 19 the total length of the object program. If you don't remember, you can see this slide. Okay, so this is how we have the formats. Okay, for this is header record. For the text record, these are the different format. Okay, so you can just check it. Okay, so start to write a header record. Start with the column 1H, then 2 to 7, 2 to 7, name of the program, it is sum. Next 3 fields you leave blank. As I told, these caps symbols just to differentiate the different columns. Next starting address, that is 101A, you fill with the 2 zeros in the beginning, and the next that is 14 to 19 contains the length of the object program. How to compute the length of the object program? This I have written here. Starting that is last address 534E, you can observe this last address 534E, last address 534E. Okay, this minus starting address 101A, it will give you the length of the object program. Yeah, length of the object program. Okay, so this is the calculation 534E minus 101A. So that calculation again you have to do it in hexadecimal. Okay, let's start with the text record. Start with the letter T. Okay, the various fields T, then 2 to 7 starting address of the object code in this text record, it will be same 101A. Then 8 and 9 column will contain the length of the object code in this text record. I will tell you how to get 1D. For the timing, while writing 8 and 9 column you have to leave blank. Okay, then start to write from 10th column onwards all the object codes that you have obtained. All these object codes you just copy. Okay, all the object codes that you have obtained till here, go on writing. Okay, with separated by this caps. Okay, those object codes that you have obtained. Okay, once you are done, you fill this 8 and 9th column. How to fill? As I told, this will indicate the length of the object code, length of this object code in this text record. How to compute? So here I have written length of the object code is 29 bytes. How we got this 29 bytes? Say you group 2 digits. As I told, all these are in hexadecimal. In hexadecimal, in hexadecimal, yeah, in hexadecimal, 2 hexadecimal digits will indicate 1 byte. Okay, 2 hexadecimal digits, 1 hexadecimal 4 bits, 1 hexadecimal 4 bits, 2 hexadecimal 8 bits. Okay, 1 hexadecimal digit 4 bits and 2 hexadecimal digits 8 bits. So 2 hexadecimal digits is nothing but 1 byte. Okay, so group, you just check 2 hexadecimal digits 1 byte. So likewise, see how many bytes: 1 byte, 2 byte, 3 byte, 4 byte, 5 byte, 6 byte, 7 byte, 8 byte, 9 byte, 8 byte. So in this way you compute, you will get a total 29 bytes. Okay, total 29 bytes. How to get? Group 2 digits, and you take it as 1 byte. 2 digits, you take it as 1 bytes, 2 digits. So totally you group in 2 digits and compute how many bytes? You will get 29 bytes, and that is in decimal. You convert it into the hexadecimal, you will get 1D. Okay, so that you are supposed to write in 8th and 9th column. Okay, so we are done with the text record. Then you see the, you have to write the next end record. The format of end record is first column contains E, then next 2 to 7 columns contain the instruction address, that is address of the first executable instruction, that is 101A. Address of the first executable instruction 101A. You can see address of the first executable instruction. You can see here 101A. How? End first. End first means it will be converted into object, end record. End first, what do you mean by first? Wherever first is there, that is first executable statement. And what is the address? 101A. So that will be stored in end record. Okay, so this is what we have. So if you have written till here, then the solution is completed. Okay, so this solution will be proper only if you have assigned the addresses properly for all the instructions. Okay, then similarly you can solve other problems which are uploaded in the Moodle, as well as they have been solved also. You just verify. I'll just tell you about the second problem. In the second problem, we have one instruction that we have not yet encountered in the previous, that is clear X. Clear X means it is the instruction that has only one operand. Only one operand. And what is that operand? It is a register operand. You can also have one more register, say for example X comma B. So how this will be that is assembled? Okay, see, in other instruction, if you see, most of they make use of a symbol, but here it is making use of X. What is X? X is a register of a SICXE machine. So if instruction is making use of a register in the operand, it will be assembled using format to addressing format to instruction format. Format 2 means it has 8 bytes, that is 2 bytes. 2 bytes. First byte contain the opcode. Opcode will be given, that is B4. And first register, second register. First register is X. The code for X is 1. Even that code will also be given in the question. Since there is no second register, it has to be filled with all 4 zeros. And this is what the object code for clear X. B410. B4 is opcode for clear X1. There is no second register, so it is 0. So this is how the clear X will be converted into the object code. Similarly, you can verify with all this. Yeah, one more here. We have one assembler directive, count word 4096. What do you mean by word assembler directive? It says that reserve only one word. Reserve only one word and initialize it with 4096. Okay, since it is given in decimal, you have to convert it into the hexadecimal, and that you have to write as a object code. Okay, and you observe here what is the location counter value. Okay, you don't increment 4096, don't increment by 4096, it has to be incremented by 3. 0015 plus 3 plus 3. Why it is plus 3? Word indicates reserve one word. One word is nothing but 3 bytes. So 0015 is added with a 3, you will get 0018, and under the object code you have to write 00130. It is nothing but hexadecimal representation of 4096. The meaning of word is reserve one word and initialize it with 130. That's all about this object program. Rest everything is same. Okay, thank you. Solve other problems also. Okay, if you have any doubt, you can clarify it. Thank you.